Hello all, welcome to the new lecture of integral equations. In the last lecture we have discussed the method of solving Fredholm integral equation which has separable kernel, in which the kernel is separable. Now we are going to discuss one illustration for the theory. So consider the Fredholm integral equation y of x is equal to lambda integral 0 to 1 minus 3x theta y theta d theta plus f of x. That is, this is a non-homogeneous Fredholm integral equation of second kind in which the kernel is 1 minus 3x theta. Discuss about the solution of this integral equation. So we know that a kernel is said to be separable if it can be written in the finite sum, a summation n equal to 1 to n, 1 to capital N, fn of x into gn of theta. That means we can write it as a finite sum of product of function of x alone and a function of theta alone. So 1 minus 3x theta can be written as 1 into 1 minus 3x into theta, like that. So f1 of x and g1 of theta taken as 1, f2 of x as minus 3x and g2 of x is theta. Then the given kernel is in this form, in the form of separable kernel. So the kernel 1 minus 3x theta is a separable kernel. Then by the method we discussed in the last lecture, we know that if the kernel is separable, then the integral equation has the solution of the form y of x is equal to fx plus lambda summation n equal to 1 to capital N Cn into fn of x, where Cn is integral a to b gn of x y of x dx. So here our Fredholm integral equation is taken as equation number 1, that is y of x is equal to fx plus lambda into integral 0 to 1 minus 3x theta y theta d theta. So this can be written as f of x plus. Now the variable of integration is d theta, so we can write the split the integral as lambda into expanding the brackets integral 0 to 1. First term is y of theta d theta minus 3x is 3x into integral 0 to 1 theta y theta d theta. Now we know that Cn is equal to integral a to b gn of x into y of x. So C1 will be integral a to b g1 of x. g1 of x is 1 into y of x dx. So integral 0 to 1 y of x dx. Or integral, since the x is a dummy variable here, we can write it as integral 0 to 1 y theta d theta. So we, instead of this integral, we name it as C1 and theta y integral 0 to 1 theta y theta as C2. Thus we have equation number 2. So this is the general form of the solution for this of this integral equation given by equation number 1. So this is the solution form. Now we have to determine these constants C1 and C2. So from the method of solving the integral equation with a separable kernel, we have already discussed that for finding or for determining the constant C1 and C2, first of all we have to multiply the equation number 2 with g1 of x and g2 of x respectively, and then integrate from 0 to 1. So first we write the first equation. So first of all we have to multiply the equation. Here g1 of x is 1 itself, so there is no need to multiply with another one. Then integrate it with 0 to 1. So we have integral 0 to 1 y of x dx. That is named as C1. So left side of the equation will be C1 equal to, in the second equation, integral 0 to 1 into f of x dx will be the first term in the right hand side. Then plus lambda into C1 into integral 0 to 1 dx. That will be 1 itself. So lambda into first integral is c1, then minus 3c2 into integral 0 to 1 x dx. Integral 0 to 1 x is x square by 2. So this will be 3 by 2 c2. So this is will be lambda into c1 minus 3 by 2 c2 like this. Now taking all the terms containing c1 and c2 into the left side, we have uh, okay, lambda they're rewriting this the first one. We will get this equation c1 equal to first lambda into c1 minus 3c by 2 c2 plus integral 0 to 1 f of x dx. Now take all the terms containing c1 and c2 into the left. Now there is c1 in the already one c1 is there. Now we are taking lambda c1 into the left, so it will be minus lambda c1. Combining that, we have 1 minus lambda into c1 plus 3 by 2 lambda c2 is equal to integral 0 to 1 f of x dx. Call it as equation number 4a. Equation 3 was the values of c1 and c2. Okay. Now the second equation is of the form. For finding the second equation, we have to multiply the equation number 2 with x, g2 of x, that is x, and then integrate from 0 to 1. So left side will be c2. It's equal to integral 0 to 1 x into f of x dx plus lambda into c1 into integral 0 to 1 x dx minus 3c2 into integral 0 to 1 x into x, that is x square dx. This we will obtain. So c2 is equal to integral 0 to 1 x into f of x dx plus lambda into this integral is 1 by 2. So c1 by 2 minus 3c2 by 3. 3 and 3 get cancelled. We have now taking c1 and c2 terms into the left, we have minus lambda by 2 c1 plus 1 plus lambda into c2 equal to integral 0 to 1 x into f of x dx. Okay, this is equation 4b. Or the two equations can be written as a system of equations as 1 minus lambda c1 plus 3 by 2 lambda c2 equal to integral 0 to 1 f of x dx and minus 1 by 2 lambda c1 plus 1 plus lambda c2 equal to integral 0 to 1 x into f of x dx. So this is the system of equations or named it as 4, which contains 4a and 4b. And this can be represented in matrix form as matrix A into C is equal to B, where A is the matrix 1 minus lambda, 3 by 2 lambda, then minus 1 by 2 lambda, 1 plus lambda, and C is the constants to be found or unknowns to be determined. So C is the matrix C1, C2, column matrix C1, C2, and B is the matrix integral 0 to 1 f of x dx, and second row integral 0 to 1 x into f of x dx. Now, according to the nature of solution of this system of equations or the matrix system, we will get the values of C1 and C2, and accordingly we will get the solution of the integral Fredholm integral equation from the equation number 2. Okay. Now consider the matrix A is equal to 1 minus lambda, 3 by 2 lambda, minus lambda by 2 and 1 plus lambda. The determinant of this matrix is denoted by delta of lambda, which is equal to determinant 1 minus lambda, 3 by 2 lambda, then minus lambda by 2, 1 plus lambda, which is equal to 1 minus lambda into 1 plus lambda, minus into minus will be plus 3 by 2 lambda into lambda by 2. So simplifying this, we will get 1 by 4 into 4 minus lambda square, and put it as equation number 6. So the determinant of the system is the delta of lambda equal to 1 by 4 into 4 minus lambda square. Now we discuss the solution of the integral equation by considering this system 5. We know that a system of equations of the form Ax equal to b has a unique solution if and only if A is invertible or determinant of A not equal to 0. Unique solution exists for the system 5 and consequently for the integral equation 1 if and only if the determinant is non-zero, that is delta of lambda not equal to 0. We know that from equation number 6 delta of lambda equal to 0 if and only if 4 minus lambda square equal to 0 or lambda equal to plus or minus 2. So, the integral equation has a unique solution if and only if the determinant delta of lambda not equal to 2, not equal to 0 or delta of lambda not equal to plus or minus 2. And this solution is obtained by solving 5 for C1 and C2 and then substituting these values in equation number 2. Now, suppose one more thing that this f of x is equal to 0. F of x identically equal to 0. Then the integral equation itself, the integral equation will be a homogeneous integral equation. That is no fx term. Fx is equal to 0 and then solution will be of the form lambda into c1 minus 3c2x. So this depends upon C1 and C2 and for finding the system will reduce us to when f of x equal to 0 the matrix B will be 0 in equation number 5 or the system is a homogeneous system reduces to the homogeneous system and we know that for a homogeneous system Ax equal to 0 x equal to 0 is always a solution, that is C1 equal to 0 equal to C2 is always a solution, and in this case this is the only solution or this is the unique solution if and only if the determinant of the matrix det A not equal to 0. So, keeping this in mind, now we have the system AC equal to 0. The system 5 becomes AC equal to 0 when f of x is equal to 0. Then we have the unique solution if delta of lambda not equal to 2, not equal to plus or minus 2 or lambda not equal to plus or minus 2 and f of x equal to 0, then the unique solution of the system is C1 equal to 0 and C2 equal to 0. Then substituting this in equation number 2, we can see that the integral equation, the unique solution of the corresponding integral equation is the trivial solution y of x is equal to 0. And we know that the delta, the determinant is equal to 0 if and only if lambda equal to plus or minus 2. So these values lambda equal to plus or minus 2 are known as the characteristic values or characteristic number or character eigen number or eigen value of the given integral equation. So in a given integral equation, if when we write the equation in the form AC equal to B where A is equal to A in the form AC is equal to B and in that case if A the matrix A has zero determinant or the values for which the determinant of the matrix becomes 0 is called a characteristic value or characteristic number or eigenvalue of the problem. So for this problem the eigenvalues are plus or minus 2. Eigenvalues are plus or minus 2. Now we will see the equation, the solution in each case if lambda is equal to plus 2 or minus 2. we can see that unique solution will exist only in the case where dit of lambda not equal to 0, delta of lambda not equal to 0. Now if delta of lambda equal to 0, lambda has two possibilities, either plus 2 or minus 2. We consider each case. Suppose we take a lambda equal to 2. So if lambda equal to 2, the equations 4a and 4b. We look at the equations 4a and 4b. Then 4a becomes lambda is equal to 2. Then 1 minus 2, that is minus c1 plus 3c2 left side 4a equal to integral 0 to 1 f of x dx. Then minus 1 by 2 lambda, that is minus c1, again plus 1 plus 2, that is 3c2. So left side of both the equations in 4 will be the same, and right side is 1 for the one equation, right side is integral 0 to 1 f of x dx, and for the second one it is integral 0 to 1 x into f of x dx. So the system reduces to in this form, while if lambda equal to minus 2, this equation becomes c1 minus c2 equal to 1 by 3 into integral 0 to 1 f of x dx. You can verify this. And c1 minus c2 is equal to x integral 0 to 1 x into f of x. Here also the left hand side are the same for each equation in equation number 8. So the equations are incompatible, they are not equal unless integral 0 to 1 f of x dx is equal to integral 0 to 1 x into f of x dx, or integral 0 to 1 1 minus x into f of x dx equal to 0. So the system has no solution, or C1 and C2, it is not possible to determine C1 and C2 if integral 0 to 1 1 minus x into f of x dx not equal to 0, or unless this satisfies the condition 1 minus integral 0 to 1 1 minus x into f of x dx equal to 0. Whereas from equation number 8 we can see that it will be incompatible unless 1 minus 3x into f of x dx equal to 0. Integral 0 to 1 1 minus 3x into f of x dx is equal to 0. If the function capital F of x is such a function that it satisfies the equations 9 and 10, then we will get, then the equation 5 or 7 or 8 are redundant, then we will have same repeating equations we will get. Okay. So if f of x satisfies the equations these 9 and 10, then we have the left side of equations 4ab. That means 7 or 8. This one, the left hand side is same, and also then the right hand side will be the same. So from this we will get redundant equations, or recurring equations, or repeating equations. Now we consider the homogeneous equation. that is f of x is equal to 0. Now if in equation number if capital Fx is equal to 0, that is y of x equal to lambda integral 0 to 1 minus 3x theta y theta d theta. Then if lambda not equal to plus or minus 2, then also system A is equal to B has a unique solution, that is given by C1 equal to 0 equal to C2, and consequently the integral equation has the trivial solution y of x is equal to 0. Now if lambda equal to 2, in the homogeneous case, if lambda equal to 2, then we have the right side is also 2, also 0. Then we have the case minus C1 plus 3C2 equal to 0, or C1 equal to 3C2 in equation number 7. So if lambda equal to 2, the equation 7 in 7 are redundant and gives the single condition C1 equal to 3C2. So we have to choose, if we choose C2 as arbitrary, then C1 depends upon C2. So we may have infinitely many values, or since the constants are arbitrary, or and consequently we may have infinitely many solutions. So for a homogeneous Fredholm equation y equal of second kind, y of x equal to 0 will always be a solution. So we have to look up to a non-trivial solution. For that we are waiting. So one condition we get if lambda equal to 2 in homogeneous equation, one condition we get is C1 equal to 3C2. Therefore, the solution will become y of x is equal to f of x is 0 plus lambda is 2 into c1 minus c2x, that is c1 minus 3c2. Equation number 2. Look at equation number 2 is c1 minus 3c2 into x. So C1 minus 3C2 into x. C1 instead of C1 we can take 3C2. So 3C2 minus 3C2x, or 6C2 into 1 minus x. So since C2 is arbitrary, we can take 6C2 as capital A, where it is a constant. A into 6 into C2, and hence it is an arbitrary constant. So the solution will be of the form y of x is equal to 1 minus x. When we take a as 1, we can say that we will get 1 minus x, and the function 1 minus x, which corresponding to the characteristic value lambda equal to 2 is called so when lambda equal to 2, the corresponding solution of the homogeneous Fredholm integral equation of second kind is y of x is equal to a into 1 minus x. So this function 1 minus x, or any convenient non-zero multiple of that function, is known as the characteristic function corresponding to the characteristic value lambda equal to 2. Or the characteristic function means it is a solution of the Fredholm integral equation, homogeneous Fredholm integral equation of the second kind, for the characteristic corresponding to the characteristic value corresponding to one characteristic value. So corresponding to lambda equal to 2, we obtained the solution, one of the solution as a into 1 minus x, which is a non-trivial solution. Okay. Similarly, we can find what happens when lambda, the solution when lambda equal to minus 2, or the characteristic function for the characteristic value lambda equal to minus 2. So when lambda equal to minus 2, we will obtain from equation 8 that C1 equal to C2. So again, the solution is of the form y of x is equal to 0 minus 2 into C1 minus 3 C1 into x, since C2 is equal to C1. So this is equal to minus 2 C1 into 1 minus 3x, where if we denote minus 2 C1 by capital B, we have y of x is equal to b into 1 minus 3x when lambda is equal to 2. So there are infinitely many solutions in this case. So when delta of lambda equal to 2 and if f of x equal to 0, then there are infinitely many solutions, and hence consequently there are infinitely many characteristic functions. So 1 minus 3x is the characteristic function corresponding to the characteristic number lambda equal to minus 2. Now in the non-homogeneous case, suppose if possible y of x is equal to fx plus capital C1 into 1 minus x plus C2 into 1 minus 3x. So that means if y of x, the solution of a non-homogeneous equation, can be considered as the sum of f of x and a linear combination of the corresponding characteristic functions. This we are going to show, going to prove. For this we have to check. First of all, compare this with the give actual solution, that is f of x plus lambda into small c1 minus 3 c2x. So fx and fx get cancelled. Then capital C1 into 1 minus x plus C2 into 1 minus 3x is equal to lambda C1 minus 3 C2 into lambda into x. Now we can write it as capital C1 plus capital C2 minus x into C1 plus 3C2 equal to lambda C1 minus 3C2 lambda x. So C1 plus C2 is equal to lambda into C1, small c1, and capital C1 plus 3 into capital C2 is equal to 3 lambda into C2. Now subtracting these two equations, we have minus 2 C2 is equal to lambda into C1 minus 3 C2. So capital C2 is equal to lambda by 2 into 3 C2 minus C1. Now of this we will obtain C2 as lambda into 3C2 minus 1 by 2, and substituting that value we get C1 as 3 by 2 into lambda into small c1 minus c2. So if we choose capital C1 as this one and capital C2 as this, we can say that the solution of any non-homogeneous system can be expressed as the sum of f of x and the linear combination of the corresponding characteristic functions. Or we can conclude that any solution of equation 1 expressible in the form is expressible in the form y of x is equal to fx plus c1 into 1 minus x plus c2 into 1 minus 3x, where c1 is equal to 3 by 2 lambda into c1 minus c2, capital C2 is equal to lambda by 2 into 3 c2 minus c1. Thus, any solution of the non-homogeneous integral equation 1 can be expressed as the sum of f of x and some linear combination of the characteristic functions. Now we discuss the non-homogeneous case, that is f of x not identically equal to 0. Then a unique solution exists if and only if lambda not equal to plus or minus 2. So if lambda equal to 2, equations 7. If lambda equal to 2 from equation 7, it is clear that uh, a unique solution exists if and only if lambda not equal to plus or minus 2. If lambda equal to 2, equation 7 shows that there is no solution unless integral 0 to 1 minus x into f of x, capital F of x equal to 0. That is unless capital Fx is orthogonal to 1 minus x over the interval 0 to 1. If lambda equal to 2, then the integral equation has no solution unless capital F of x is orthogonal to the characteristic function corresponding to lambda equal to 2. Hence, if lambda equal to 2 and the function fx is orthogonal to 1 minus x, then from equation 7a we have c1 is equal to 3c2 minus integral 0 to 1 f of x, capital Fx dx. Uh, So if lambda equal to 2, then the function f of x is orthogonal to 1 minus x. Then from the equation 7a1, from one of the equations we can write c1 as 3c2 integral 0 to 1 f of x dx. So we have y of x is equal to capital Fx plus 2 into 3c2 minus integral 0 to 1 f of x dx minus 3c2x. This is equal to fx plus 2 into 3c2 into 1 minus x minus 2 into 0 to 1 f of x, or this is equal to fx minus 2 into integral 0 to 1 dx, capital Fx dx plus a into 1 minus x, where a is an arbitrary constant equal to 6c2. And this implies that the integral equation has infinitely many solutions. And similarly, if lambda equal to minus 2, there is no solution unless f of x is orthogonal to 1 minus 3x over 0, 1, in which case um, infinitely many solutions exist as follows. So when lambda equal to minus 2, from equation 7b we can rewrite c1 and c2, or we have y of x is equal to capital Fx minus 2 by 3 integral 0 to 1 capital F of x plus b into 1 minus 3x, when integral 0 to 1 minus 3x into fx equal to 0 will be equal to minus 2 c2 is an arbitrary constant. So this is about the nature of solutions of the given problem. Okay, let's stop here. Thank you. Thank you all.